Good afternoon, everyone. My name is Leo, and I'll be presenting our work, Fair-CO2, Fair Attribution for Cloud Carbon Emissions. This work was done at Cornell in collaboration with the University of Pennsylvania. Currently, cloud computing accounts for an estimated 2.5 to 3.7% of global carbon emissions. And that is more than both the aviation industry and the shipping industry, making cloud computing a major climate change culprit. The carbon footprint of data centers can be divided into two major components. The first major component is embodied carbon, comprising the carbon emissions associated with capital expenditures. They're emitted during the manufacturing process for equipment like servers. And the second component is operational carbon, comprising the carbon emissions from the energy used to run those servers. Although we can estimate the carbon footprint of servers with methods like lifecycle analysis, estimating the carbon footprint of a single workload is much more difficult, and it can come with unique challenges due to the cloud dynamics of how workloads share the underlying resources. Workloads perform different tasks, run with different colocation partners on different servers, run at different times, and use different amounts of resources. Yet it is important to provide accurate carbon footprint estimates for individual cloud workloads because accurate carbon attribution allows cloud users to track their sustainability goals. It provides the necessary feedback so that users can optimize their workloads to be more sustainable. Moreover, accurate and fair carbon accounting is necessary to support important economic policies like carbon pricing. In response to the need for cloud carbon attribution, cloud providers like Amazon, Google, and Microsoft have come out with carbon dashboards that provide carbon footprint estimates for cloud users. Moreover, papers and tools have also been published by academics and nonprofits. Before we go further, let's talk about what we actually want in a good cloud carbon attribution method. First, we want it to be fair, and that it accounts for the complexities of cloud dynamics. Second, we want it to be scalable, so it can be feasible at cloud scale. Third, we want it to be actionable, so that it can enable users to optimize their carbon footprint of their workloads to be more sustainable. With the importance of accurate carbon attribution for cloud workloads in mind, I will next talk about what the current methods are. I'll show, although scalable, they are unfair and provide delayed attribution, which hinders the ability to optimize workloads. I'll then discuss how the Shapley value, the gold standard for solving difficult carbon attribution problems, can be applied to cloud carbon attribution. However, the Shapley value is not scalable due to exponential computational costs. Moreover, it also provides delayed carbon attribution. I'll present our solution, Fair-CO2, which is a system for cloud carbon attribution that is both fair and scalable, and it can provide immediate carbon attribution, enabling effective user workload optimization. First, let's take a look at existing methods. Current methods, such as those proposed by Google and the Green Software Foundation, attribute carbon proportional to workload resource usage. To demonstrate how this works, let's say we want to attribute 100 kilograms of carbon from a set of CPUs to a set of workloads that use those CPUs in a set of period of time. We can look at each workload's CPU usage in terms of CPU hours and then attribute carbon to the workload's share of total CPU usage proportionally. This simple amortization method is easily scalable. However, current methods are unfair because they ignore cloud dynamics. First, they ignore how resource demand changes over time, and second, they ignore interference between workloads. Let's first look at how resource demand can lead to unfair attributions. Embodied carbon scales with the quantity of resources. The more servers, the more carbon that was emitted to manufacture them. In the ideal scenario, there will be constant demand, allowing for perfect provisioning and no idle resources. However, real resource demand varies more over time. In both scenarios on screen, the minimum required resource capacity is actually the same, and that is because in the variable demand scenario, that required resource capacity is determined by the peak demand. However, current cloud carbon attribution methods attribute peak versus off-peak usage the same, even though they have markedly different effects on the required resource capacity and thus embodied carbon. Now let's look at how interference can lead to unfair carbon attributions under existing methods. Because current methods attribute carbon proportional to resource use over time, interference from co-location neighbors can lead to unfair increases in resource use and thus carbon attribution. Through co-location profiling of 15 diverse workloads, we found that workloads differ significantly and how much interference they caused their neighbors, and how sensitive they were to interference themselves. For example, when we run Embody and Convex Call, two workloads from the PBBS workload suite together, Embody experiences an 87% increase in runtime and resource use compared to if we were to run in isolation. But if we take that exact same Embody workload and we run it with another database workload, it only increases in runtime by 18%. That means for the exact same workload, we see a 60% change under current methods in carbon attribution. In addition to being unfair, current methods provide delayed attribution, hindering workload optimization. And that's because current method must attribute retrospectively. We need to tally up all the resource usage over a period of time first. Many cloud carbon attribution dashboards by the hyperscalers attribute carbon at a monthly granularity, meaning that there can be up to a 1-month delay between cloud usage and getting a carbon footprint estimate back. This long delay in getting carbon footprint feedback makes it difficult for users to optimize their carbon footprint. We see that current methods are scalable but unfair and not actionable. Fortunately, there is a solution to the attribution fairness problem. I will now talk about how the Shapley value, the gold standard for solving fair attribution problems, can be applied to cloud carbon attribution for workloads. The Shapley value is a game theory solution for complex fair share cost attributions that has been applied to a wide variety of domains like infrastructure cost sharing, law, and computer systems. Without going into the details, the Shapley value has 4 main key properties for fairness: symmetry, null player, efficiency, and linearity. To see how the Shapley value is done, let's take a look at an example where we have 3 workloads, A, B, and C. We want to find what is A's share of the total carbon footprint of these 3 workloads. The Shapley value looks at A's marginal contribution to the carbon footprint across all the workload permutations, and there are 6 permutations of these workloads. For each permutation, A's marginal contribution is equal to the marginal change in carbon footprint when A is added in the order of the permutation. And then we can average across all these marginal contributions to get the Shapley value, which is A's fair share of carbon footprint. Through using marginal contributions, the Shapley value accounts for cloud dynamics, filling in the gap that current methods have. It accounts for peak demand because we can look at the marginal change in the peak demand of a resource when a new workload is added. It accounts for interference because we can look at the marginal change in total resource use across the system, including in co-location partners that arise as a result of additional interference. But there's a catch. The Shapley value is not scalable. We need to profile 2 to the n possible combinations for n workloads, meaning that the computational cost is exponential. Moreover, the Shapley value is again retrospective, meaning there can be a long delay between cloud use and getting carbon footprint feedback, leading to difficulties in optimizing workloads. Now that we've seen how current methods, although scalable, are unfair and provide delayed attribution, and we've seen how the Shapley value is a fair ground truth but not scalable, I will now propose our solution, Fair-CO2, a system for fair carbon attribution that approximates the ground truth value while being able to scale to millions of workloads. It also provides immediate attribution, enabling dynamic workload carbon optimization. In a cloud data center, we can monitor aggregate resource demand, workload telemetry like CPU and memory usage, node telemetry like static and dynamic power. With these as our inputs, we want to get to a fair carbon attribution for both embodied carbon and operational carbon. And Fair-CO2 does this with 2 core components. The first core component being temporal Shapley, which takes an aggregate resource demand and then uses the Shapley value to dynamically adjust the rate of embodied carbon attribution in the form of something called embodied carbon intensity. The second core component is the interference adjuster, which takes in workload telemetry along with historical co-location data to build an image of how each workload responds and deals out interference, and then uses that to adjust resource costs to offset the unfair effects of interference. Adjusted resource costs multiplied by the embodied carbon intensity gives the embodied carbon attribution, while adjusted energy costs multiplied by the grid carbon intensity gives the operational carbon attribution. Let's first take a look at how temporal Shapley accounts for peak demand. Rather than using the Shapley value to allocate and attribute carbon across workloads, we can instead attribute carbon across time blocks via the Shapley value. For example, we can take a 30-day trace of CPU allocations and split it into 10 3-day time blocks, and then use the Shapley value to find each time block's fair share of contribution to the peak demand, generating a demand-adjusted rate of embodied carbon attribution at a 3-day granularity. And we can break it down even further, breaking down each 3-day time block into 8-hour time blocks, and doing the same Shapley value calculation again to generate an 8-hour granular embodied carbon intensity signal. And we can do that again at a 1-hour granularity, generating finer granular embodied carbon intensity signals. The temporal Shapley is scalable. By using time blocks as players in the Shapley value calculation, the computational cost no longer scales with the number of workloads. Moreover, through a hierarchical decomposition approach, we'll limit the exponent and the exponential cost of the Shapley value calculation. The second core component of Fair-CO2 is the interference adjuster, which adjusts resource cost allocations to workloads to offset the unfair effects of interference. The interference adjuster accounts for interference effects by looking at historical collocations of a workload and using that to characterize our workloads in terms of alpha, which is sensitivity to interference, and beta, which is a workload's propensity to cause interference. We can then use that to generate an attribution factor by multiplying alpha and beta with the workload's resource allocation, and attributing an adjusted resource cost based on the attribution factor. This method scales linearly with the number of workloads, making it scalable. We use Monte Carlo simulations to evaluate both Fair-CO2 and baseline current methods. Across 10,000 randomly generated scenarios of workload collocations and 10,000 randomly generated scenarios of dynamic demand, we apply the ground truth Shapley method, the baseline current methods, and Fair-CO2 to generate per workload carbon attributions. We then compare the baseline and Fair-CO2 against the Shapley value ground truth, using percentage deviation as a measure of fairness. Across the simulation scenarios, we looked at overall fairness. We also looked at how Fair-CO2 scales with the length of time, with the number of workloads, historical data availability, and with varying grid carbon intensity. Across these cases, Fair-CO2 is able to reliably provide fair carbon attributions that come close to the fair ground truth. We also show that Fair-CO2 eliminates the unfair biases from workload type on carbon attribution, where some workload types would get particularly unfair attributions under the current schemes. This is a summary of the results. On the x-axis, we have the absolute percentage deviation from the ground truth as a measure of fairness, and as 0, we have the ground truth. Current methods deviate from the ground truth by 80% on average due to dynamic demand effects and 9.7% on average due to interference effects. In comparison, Fair-CO2 attributes significantly closer to the ground truth, and 19% average deviation for dynamic demand scenarios, which is a 4x improvement, and at 1.72% average deviation for collocation scenarios, which is a 5.6x improvement. However, we still have not addressed the problem of attribution being retrospective. Attribution can only happen once we have the resource demand trace, meaning that workload running here must wait until the end of the attribution period, hindering optimization potential. But what if the workload wants to know its carbon footprint right away, or even before running? Fair-CO2 enables with demand forecasting and live carbon intensity signals. Carbon attribution then becomes immediate, allowing for easier optimization. Let's demonstrate this process with FICE, the vector similarity search workload used in retrieval augmented generation. The goal here is to minimize workload carbon footprint while meeting an example performance constraint of a P99 tail latency being less than 2 seconds, a typical tail latency requirement for large-scale LLMs. We can do this with dynamic workload optimization using live carbon signals from Fair-CO2. To characterize the options available for workload optimization, we look at how different knobs like CPU core allocation, query batch size, and index search algorithm all affect tail latency and carbon footprint. Sweeping across these different values for these knobs, we can generate a Pareto front of configurations for different carbon intensities. To meet our goal, we want to choose the lowest carbon configuration that still meets tail latency requirements. The interesting thing is that depending on the carbon intensity, the best choice can actually change. This means that in response to varying grid carbon intensity and varying embodied carbon intensity from Fair-CO2, we can dynamically optimize our workload configuration to minimize the workload's carbon footprint. For example, is denoted by the different color blocks. We will want to switch between different index search algorithms in response to live carbon signals. Doing so can net significant carbon savings against options like optimizing purely for performance. To bring it all together, we looked at how current resource utilization proportional carbon attribution methods are scalable, but fail to account for cloud dynamics like dynamic demand and inter-workload interference. To address this, we can use the Shapley value, a game theoretic solution that is the gold standard for fair attribution problems. However, the Shapley value calculation scales exponentially and making it unscalable. Moreover, both the ground truth and current methods can only provide delayed attribution, which prevents effective workload optimization. Thus, we propose Fair-CO2, a system that is both fair and scalable, and it does so with two core components: temporal Shapley, which does demand-adjusted attribution, and the interference adjuster, which accounts for workload interference. Fair-CO2 using demand forecasting can also provide immediate carbon attribution, enabling dynamic optimization. Please read our paper and look at our artifact if you're interested in more details. Thank you for your time and interest in our work. I'd be happy to take any questions right now.